Let's do that. Okay, so those are some definitions associated with sequences. So keeping in mind that a sequence is just a pattern of numbers separated by commas. We've got our notation for sequences. We subscript them. Arithmetic sequence is a sequence generated by a constant sum or difference. And then the common difference is what you're asked to find. Usually that's how you figure out what the next number in the sequence is by knowing the common difference. And then knowing that connection between arithmetic sequences and linear functions. The common difference, d, is just the m in the slope. Okay. And then the y-intercept is where we start. All right, geometric sequence is generated by a constant product or quotient. You can test to see if a sequence is geometric by taking one term and dividing it by the previous term, and then keep doing that and show that it's a common ratio between a couple different pairs at least. So sequence generated by a constant product or quotient. And we call that constant product or quotient the common ratio. So it's the number that you multiply one term by to get to the next term, and then that term to get to the next term. And then keeping in mind that geometric sequences grow in the same way that exponential functions do. So exponential functions can be used to model those. We can generate sequences, so this goes for whether they're arithmetic or geometric, but we can generate sequences with a formula. An explicit one would be like a sub n equals. So it's a sub n equals, and then you fill in the blank. You say what to do as you go from one term to the next. N is representing the counter. So a sub 1 would be the first term, a sub 2 is the second term, a sub 3 is the third term, and a sub n is the final term if it's a finite sequence. So explicit formula would be a sub n equals, and then you fill in the blank. Whereas a recursive formula has two parts to it. They tell you what the first term is, and then they tell you how to get the next term based on the first term. So you'll do something to the first term to get through the next term. So our goal today is just to be able to identify the sequences, arithmetic, geometric, or neither, and then if it's arithmetic or geometric, what would the next term be, or the next 5 terms be, or whatever. Just looking at patterns. All right, so you're going to be asked to write out the first 5 terms. Did you see this notation with the fancy brackets? Did you see that last year at all? Or no? Wasn't it? This textbook uses, they just use the fancy brackets around the a sub n. Did you have it without them maybe? So that's what they use in here. But same deal. But a sub n equals n minus 1 over n. What we're going to do is find a sub 1, 2, 3, 4, and 5. So it works like this. It's literally a sub 1 equals 1 minus 1 over 1, which is 1 minus 1 is 0, 0 over 1 is 0. And then you go to a sub 2. And so that'll be 2 minus 1 over 2, which equals 1/2. And then a sub 3, which would be 3 minus 1 over 3, or 2/3. What do you think the next two in the pattern are going to be? What's a sub 4 going to be? A sub 4 will equal 3/4, and then a sub 5 will equal 4/5. Yeah. So, you know, you can usually think about the first few and then continue the pattern, or keep plugging in values of n. So they subscript b here. B sub n is, this is just n if n is even. So n if n is even. So it's itself, if it's like, so b sub 2 will be 2, b sub 4 will be 4, b sub 6 will be 6, but it's 1 over n if n is odd. So b sub 1 is going to be 1 over 1, or 1. B sub 2 is 2. B sub 3 is 1 over 3. And then b sub 4 is 4, and b sub 5 is 1 over 5. So those are the first 5 terms of that sequence as described. That's described explicitly. Each of these 3 are described explicitly. And then I put the third one in here just so that we're sure we understand what this -1 to different powers will do. That'll make it alternate signs. So that's how you alternate signs in a sequence. You may have seen one before that alternates signs. It goes from one term to the next. But if I plug in 1 here, 1 plus 1 will give me 2. -1 to the second is a positive number. And then if I plug in 2 here, it's going to be odd, so that'll change it to negative. So it's going to flip-flop signs. So first one looks like this. We have c sub 1 equals -1 to the, let's do this, just show you the first couple, and then we'll see if we can see the pattern. So -1 to the 1 plus 1 times 2 over 1. So the -1 to the second power will be positive, and then that just equals 2. And then c sub 2 equals -1 to the 2 plus 1 over, or times 2 over 2. So I'm placing a 2 everywhere I see an n. And -1 to the third power will be a -1. 2 over 2 is 1, so this becomes just -1. And then c sub 3 is -1 to the 3 plus 1 times 2 over 3. And so -1 to the odd power is going to be a negative, and this will end up being -2/3. And then c sub 4 is -1 to the 4 plus 1, 2 over 4, which equals, oops, I have the wrong power on here. It should be positive. It should be +2/3. And then we're back to negative here. So to the 5th power will be negative. Negative times 2/4 is -1/2. And then c sub 5 would equal -1 to the 5 plus 1, 2 over 5. So now it's back to positive. It's 2/5. So you're literally just plugging in 1, 2, 3, 4, up to however many terms you want in for n, and then evaluating it. So you got to get familiar with that notation. All right, it says write out the first 5 terms of each recursive formula. So this first one says start with 1. So we're going to just start with 1 here. And then the s sub n equals n s sub n minus 1. What it says to do is take, for the second term, we're going to put 2 in for n. And that equals 2 times s sub 2 minus 1. And what you'll see here is I end up with 2 times s sub 1. Well, s sub 1 is the previous term. So it's just telling me to take 2 times s sub 1, which was 1, and then that gives me my second term, 2. And then when I'm ready to get s sub 3, s sub 3 would equal 3 s sub 3 minus 1, which is 3 times s sub 2. And S sub 2 is my second term's value. So my second term's value is 2, and so I end up with 6 here. So we can get here the next couple terms. Move this down. So S sub 4 times S sub 4 minus 1, which is 4 times S sub 3, 4 times 6. The fourth term is 24. And then S sub 5 equal 5 times S sub 5 minus 1, which equals 5 times S sub 4, which equals 5 times 24. You end up multiplying by the next number up each time, so it's 120. And these sequences are not necessarily, they're not arithmetic nor geometric. They're their own sequence here. This next one, I think you'll recognize it. The first two terms are 1, 1. The third term, u sub 3, is going to be equal to u sub 3 minus 2 plus u sub 3 minus 1. So u sub 3 minus 2 plus u sub 3 minus 1, which is u sub 1 plus u sub 2. So what this is saying is that you get the third term by adding the previous two. So 1 plus 1 is 2. And then you're going to get the fourth term. It's equal to u sub 4 minus 2 plus u sub 4 minus 1, which is u sub 2 plus u sub 3. So I'm going to add the second and third terms to get 3. You recognize this sequence? Have you seen this one before? This is the Fibonacci sequence. Okay, so u sub 5 would be adding these two terms, the previous two, which would be 5. Right, so sequences defined recursively and explicitly. These are explicit up here. These are recursive. I'm just going to ask you just to generate the next few terms, and then we'll get into adding up the terms, deciding if it's arithmetic or geometric. All right, so determine if the following sequences are arithmetic, geometric, or neither, and list D or R if appropriate. So I don't know if you could tell in these just by looking at it. Sometimes it's not as obvious. That's what we test pairs. If it's not as obvious, you look at the next term and its previous term, the next term after that and its previous term, and look for a pattern. That's kind of what we're doing here visually at the top. Whether it says that or not, that's what I'm doing in my head, is looking at this term and then how it compares to the previous, this term, how it compares to the previous. Right away, I think you can usually tell if it's arithmetic or not. You can tell quickly on that first one it's not arithmetic. It's jumping by quite a bit. So what do you think? First one, is it arithmetic, geometric, or neither? It's geometric. What can you see its common ratio? Yeah, it's geometric. We've got R equals -3. The next one is arithmetic. Tried to hide it a little bit, but pretty easy to see. Arithmetic, and we call D equal to 1/2. And then here it's not arithmetic. It goes up by 1, and then by 2, and then by 3, and then by 4. It's not arithmetic because the D is changing. It's not geometric because you can't multiply by a common factor and get to the next term and the next term and the next term. There's a way to test that. You would look at 10 over 9. Does that equal 12 over 10? no. So right there you could stop and say it's neither. And if for some reason it's not terribly obvious, I think these down here are pretty obvious too. We can use the method of testing pairs. So you look at, say, usually what we do is we test to see if it's geometric, maybe first. If you don't see that, this one I think is pretty easy to see it's arithmetic, but you just look at -1 and 3, and it's either testing to see if there's a common ratio or a common difference. But here, -1 minus 3 equals -4. -5 minus -1 is also -4. So we're testing pairs, and then just to be sure, you can go -9 minus -5 also equals -4. So this is arithmetic, and D equals 4. So that's what we mean by testing pairs. The second one, you'd go -9. It's clearly not arithmetic. So test pairs by looking at quotients. -9 over 3 is -3. 27 over -9 is -3. And -81 over 27 is -3. So this is geometric. And R equals -3. What about the third one? If you start testing pairs, like 4 over 8, what does that reduce to? 1/2. 2 over 4 is... Okay, so far it's looking good. What about 1/2 over 2? What does that equal? This would be the same as 1/2 times 1/2, or 1/4. So when I go from 2 to 1/2, it's not the same ratio as the 2 over 4 and the 4 over 8. So this is the neither. So as you're testing pairs, if you see any pair in the list that do not reduce to the same value, it's neither. So you got to test more than just 2. So look at it a little more carefully. All right. You guys familiar with factorials? Just a little bit. Maybe a little bit with combinations and permutations at all. Okay. So we're going to bring back, when we get to the end of this chapter, we're not going to get into combinations and permutations. You may have done that in your probability unit in AP Stats, a little bit of that. But we will use that combination number, that n choose r number, as our coefficient when we're expanding out a binomial using the binomial theorem. I'm going to show you how to do that. We may have talked about that last year, but that's equivalent to looking at a specific row of Pascal's triangle. It's just you don't have to build the whole triangle to get to that row when you use the formula. So a couple things about factorial. 0 factorial, these are all too close together. 0 factorial equals 1. These aren't all equal to each other. That's what it looks like. So 0 factorial is defined to equal 1. 1 factorial is equal to 1. And then n factorial is equal to, remember how it works? Like, what's 3 factorial equal to? 3 times 2. Yeah, 3 times 2 times 1. So it goes n times n minus 1 times n minus 2, etc. Okay, is the way you think about that. Why is 0 factorial 1? That's just how it's defined. If it's not defined that way, then we'd have division by 0. Look it up. I don't remember. To get back to you. That would be a project for you. It would be hard. Probably at your fingertips. But I don't remember why. But it's defined as 0 factorial equals 1. Otherwise, we have division by 0 when we do combinations or permutations. I don't know if you remember the formula for it, but if you have combinations, permutations, you have a subtraction in there, and you can end up with a 0 when you subtract the numbers. We'll look at that when we look at the binomial theorem. And then summation notation. Before we get into series, which is the sum of the terms of a sequence, we should be familiar with this summation notation. For some reason on here, it wouldn't, when I transfer this over, it didn't do it the way in which I'd like it to be done. This 10 should be on the top, the k equals 1 on the bottom, but it looks like this. We've got k equals 1. K is the counter up to n. N is the finite ending point of a sub n. And so we're going to start at 1 and then count all the way up to n. And you have a formula here, and you're just plugging in values 1 and then 2 and then 3. So the way it works is this. And this really should look like this. You should have the k equals 1 down here, the 10 up here. I don't know why it came through like that, but it did. So what this would mean is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8 plus 1 over 9 plus 1 over 10. It should be a pain to add up, even typing it all into the calculator. You could do that. You could type all 10 fractions in and add it up. But there's a mode on the calculator. I'll show you in just a minute on how to do that. So you should be able to, given summation notation, be able to write out the terms and then literally be able to add them up. If there aren't too many of them, just add them up on your head or on the calculator. And then also on the calculator, use the sum sequence to add them up. I'll show you how to do that in just a minute. You should also be able to go backwards on this. So this one would be, if I draw my little sigma, to go from k equals 1 to, what's this going up to? 9, yeah. Plugging in 1 through 9. And the equation would be, in terms of k here, k squared. So you have 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to 9 squared. So this is the shorthand way, or sigma notation way, of writing this sum of squares. And then down here on number 6, you don't need to add all these up on your calculator. You could. I'll show you how to do it on the calculator. So here's what it looks like. By the way, if you go to mode here, here is, so we've done function mode, we've done parametric, polar, and now we're in sequence. So you can change it to sequence mode. And in sequence mode, if you go to y equals, you can graph the sequence. So we could graph the sequence 1 divided by n. And this thing calls for u sub 1. U sub 1 would be 1. U sub 2 would be 1/2. And then you could graph it. So it's a bunch of dots there. If you go to second and then stat, second stat menu, so you have to remember it's second stat menu. It's not under the math menu. And you go over to options here, or operations. I think it's operations. And you'll see sequence right here. So select sequence, although I think I'm still in the graphing mode. So let's quit out of there. So if you go to second stat, go over to operations, select sequence number 5. Oh, this is going to be different. So I apologize. Some of you guys have the classic mode, and so it's going to actually come up with parentheses. I may have to do it twice. I haven't used it in this mode, but here, sequence. So we would have the expression is 1 divided by n. When it pastes it, you'll see what it should look like in classic mode. And then the variable is n, and then the start, so you want to start at 1 and then end at 10, I think it was. Step was 1. So step just means what it's going up by, which is typically 1. It should have a default of 1. And then let's see what it does when it pastes it. So if you're in classic mode, oh, okay, what this is going to do for sequence, I'm gonna have to change it back to classic mode. I'm not sure if I remember how to do it or know how to do it in this mode. But what this will do, I believe, is list the first 10 terms of the sequence. And if you want the sum of the sequence, you need to add in the word sum before it. So what this does is it lists all the terms of the sequence. I think if you go to math on here, math and fraction, you hit enter. There they are. Does that look better? It's like what we had written, right? So 1, 1/2, 1/3, 1/4, 1/5, etc. Let me see if I can change it back. Change it to, I am in Classic, okay. I'm in Classic, but it just is set up differently. So if you have the TI-83, it's set up a little differently. I may have to help you on an individual basis. But if I want to add all those up, what I can do here is if you go to second list, you'll see under math, there's number 5 is the sum. So number 5 is the sum. And then you got to go to second, stat, operations, and then sequence, and type in all the same stuff. So let me hit paste. And then finish your parentheses. So on the TI-83, if you're truly in classic mode where it's not asking for the prompts, you'll have to go to second list, math, and hit sum first, and then sequence. And these are the 4, I believe there are only 4 terms you put in on the classic. I think you just need to put in the expression, which is 1/n, the variable n, and then 1, 10, and I believe the step, the default is 1, so I don't think you have to put in the step. You have to try it, but I believe when I did it on the older calculator, I did it earlier today. I don't remember putting in the step. I think the default is 1, okay, because typically we count by ones with sequences. And then you hit enter, and it will give us the sum. And then if you hit math, and then fraction, it will give you the sum as a ratio of 2 numbers. So 7,381 over 2,520, which is nice because the original was in fraction form. So it's nice to give a solution in fraction form. And if you want to, you can check me. You can try 1 plus 1/2 plus 1/3 and type all those out, and you get the same number, that 2.92896. So 7381 over 2520. So the calculator will do that sum for you. I think the ones I give you for practice on the homework, I don't remember even using the calculator's function on that. You should know how to do it. Show how to graph it and also how to get the sum. And that's about it. So any questions on that? And I can help you on the TI-83 if you need help.